I'm Herb Gross, and welcome to lecture number 34 in Gateways to Algebra, where today we're going to discuss something called the Pythagorean Theorem, a very nice result from geometry that has many practical applications. But before I do that, I wanted to make sure that I didn't leave a misconception after the last lecture. I want to go back to the idea of finding two numbers whose product is a constant term and whose sum is the coefficient of x. See, what I want to point out was, look, suppose I have an equation like x squared plus 4x minus 6 equals 0. I can complete the square here. I can use the quadratic formula. But suppose I go back to the so-called easy way, the one we were looking for before. We say, let's factor this into x plus a times x plus b. And what must happen over here? A plus b must be 4, okay? But a times b must be negative 6. So the point is we now have to look for two numbers which when multiplied together give me negative 6, but which when added together give me positive 4. Now there are no two whole numbers that do this, but what I want you to see is there are two numbers. I'm not going to go through this. If you do this problem by completing the square, or by completing the square, you'll be amazed to see where these came from. But look at this. Suppose a was 2 plus the square root of 10, and b was 2 minus the square root of 10. What would happen if I add a and b here? Wouldn't the 2 plus 2 give me 4, and the square root of 10 and negative square root of 10 would cancel out? In other words, with these choices of a and b, wouldn't a plus b be 4? Now what about if you multiplied here? This is the sum and difference of the same two numbers. 2 plus the square root of 10 times 2 minus the square root of 10 is going to be, this is the a squared minus b squared. This 2 times 2 is 4, minus what? The square root of 10 times the square root of 10, well that's just 10, and 4 minus 10 is negative 6. So these two numbers actually do work. You see, the point I wanted to make sure you understood is when I said that we can't find two numbers whose product is the constant term and whose sum is the coefficient of x. They do exist, but they're extremely difficult to find by trial and error. And that's the only point I wanted to make sure you understood. That's the advantage of using either completing the square or the quadratic formula, or at least one of the advantages. Now what I wanted to do is to get back to what we call the Pythagorean Theorem. And the Pythagorean Theorem gives us a relationship between the three sides of a triangle when the triangle has what we call a square corner, a 90-degree corner. There's always a relationship between the sides of the triangle, but in a right triangle, one that has a square corner, the relationship is kind of nice. Let's just look at a general triangle to begin with. See, if I take any triangle, suppose I have a triangle and one side is 8 inches, one side is 12 inches, one side is 11 inches. Nothing special about this. About the only thing I can be sure of is that if I add up any two of these lengths, it must be greater than the third one. You see, the shortest distance between 2 points is a straight line that joins them. So the shortest way of getting from A to B is to go along the straight line that connects A to B. Obviously, A to C plus C to B must be more than A to B. So there are relationships that involve the sides of a triangle, but the one I want to look at, special case I want to look at, is called a right triangle. That means it has a square corner. And okay, now there's some special names given. The two sides that make up the square corner are called either the legs or the arms or the sides. And the side that's opposite the square corner is called the hypotenuse. And there's a very nice relationship between the hypotenuse and the other two sides of a right triangle. And you'll see why I bring it up under quadratic equations, because what it says geometrically is, if you were to draw a square on the hypotenuse, and then draw a square on each of the two sides, that the area of the two squares on the sides would be exactly equal to the square on the hypotenuse. In other words, stated algebraically, if you square the length of this side, square the length of this side, and add them, you get the square of the length of this side. So the Pythagorean theorem says, see, Pythagorean theorem says that a squared plus b squared equals c squared, where c is the hypotenuse and a and b are the two sides. By the way, there's a very cute proof of this that I thought I would share with you. Not that I have to give you the proof, but if I give you the proof, it'll make this whole thing seem more plausible. See, what we're going to do is, let's make a smaller diagram so we can get everything into one diagram over here. Let's take a right triangle, one of whose sides is A, the other side is B, the hypotenuse is C, and let the area of that right triangle be denoted by T. I'm going to show you a rather nice thing. What we're going to do is we're going to draw a square whose side is A plus B. So we're going to draw a square whose side is A plus B. And I'm going to subdivide it in two different ways. And rather than superimpose them on the same diagram, let me just draw the same diagram twice. Here's what we're going to do. After I mark off A and B this way and A and B this way, I'm going to draw this line, and then divide these two rectangles into triangles. Look what happens over here. Isn't each of these four triangles the triangle I have over here? Look at each of these four triangles. What do they have? The two sides are A and B, and they have that square corner. So in other words, what happens over here is take a look at what happens when I break up the square. There's one piece that's A by A, so the area of that piece is A squared. I'll write it bigger so you can see it better. Then this little piece over here, the area is B squared. Now we have these four triangles, and each of the triangles has area T. So what's the area of this square? It's A squared plus B squared plus 4T. Now what we're going to do is break the square up slightly differently. This time, we're going to get the hypotenuse to come down like this. In other words, what we're going to do is we go from the long side, short side, long side, let's see, long piece, short piece, long piece, short piece. See what I'm doing? I'm laying the triangle off along the edges this time. See, the A and B make up the sides of this triangle. So what happens over here? Each of these sides over here is the hypotenuse. So what do we have here? We have four triangles, and the area of each triangle is T, so that's 4T. And what do we have over here? We have a square whose side is C, so the area is C squared plus 4T. Now the point is, I've computed the same area in two different ways. Since a square has only one area, if this is the right answer and this is the right answer, these must both be different ways of saying the same thing. By equating these two, let's subtract 4T from both sides. And what do we wind up with? A squared plus B squared equals C squared. And again, let me show you how that works. I think it's a very, very nice result. Far from self-evident, but let's just get used to it. And by the way, if you ever want to check some of these results out, just draw them to scale. In other words, if you want, draw a 5-inch line with a protractor, make a square corner, then make a 12-inch line, or draw it to scale, then connect these points and actually measure the length and see what happens. But see, suppose I know that one side of a right triangle is 5, another side is 12. I want to find the length of the hypotenuse. So one side squared plus the other side squared has to equal the length of the hypotenuse squared. So 5 squared plus 12 squared has to equal x squared. That says 25 plus 144 is x squared. 25 plus 144 is 169. So x squared has to be 169. So x must be the square root of 169, which turns out to be 13. So if the two sides of a right triangle are 5 and 12, the hypotenuse has to be 13. See, notice, by the way, there are lots of triangles, two of whose sides will be 5 and 12. In other words, imagine these to be the hands of a clock. This is 5, and this is 12. As time goes on, these hands move, don't they? But this is still 5 inches long, this is still 12 inches long, but as this hand moves, doesn't the length of the line that joins the two hands change? See, in other words, this nice result only holds when there's a square corner over here. By the way, notice, let's just do another one. They won't always come to be whole numbers. Let's suppose that we'll call the base the side the triangle is standing on, and we'll call the height the one that makes the square corner over here. So suppose the base of the triangle is 8, and the height is 9. And we now want to find the length of the hypotenuse. See, the Pythagorean theorem still says what? The square of the hypotenuse, x squared, equals the sum of the squares of the other two sides. 8 squared plus 9 squared. 8 squared is 64, 9 squared is 81. So x squared would be 64 plus 81, which is 145. So x would be the square root of 145, which to 2 decimal place accuracy would be, that's what that little dot means, I've rounded off, would be 12.04. And in most cases, you could say it's about 12. And again, you could check that out if you wanted to. So you get the idea how this thing works? Now, of course, again, you still have to know some of our rules of algebra. What if we were given the hypotenuse? See, instead of being told that one of the sides is 8 and the other side is 9, Suppose we were told that one side is 8 and the hypotenuse is 9. By the way, can you see that the hypotenuse is the longest side of a right triangle? But how does this thing work? The square of the hypotenuse, 9 squared, equals the sum of the squares of the other two sides, x squared plus 8 squared. That would say 81 is equal to x squared plus 64. Now subtract 64 from both sides. That says that 17 is equal to x squared. Now take the square root of both sides. That says x is the square root of 17. So x would be what? Approximately 4.12. But it would be exactly the square root of 17. The rounding off comes when we express the square root of 17 as a decimal. See, by the way, let me just make sure you understand that. When we say that the square root of 17 isn't exact, we mean it's not exact when you try to express it as a decimal. The square root of 17 is certainly exact. It's exactly that number which, when multiplied by itself, gives you 17. See, 4.12 times 4.12 doesn't give you 17, it gives you something close to it. So 4.12 is close to the square root of 17. But what is the square root of 17 exactly? It's exactly that number which, when multiplied by itself, gives you 17. The trouble is that when you try to write that number as a decimal, the best you can get is an approximation. Okay? Let me show you how this comes up in graphing. You see, suppose you're dealing with a straight line. Suppose I have a line, suppose I have 2 points in the plane, and P is the point 2, 3. That means what? 2 to the right and 3 up. And suppose Q is the point 3, 7, which would be 3 to, as if I've, make sure I'm reading this thing, right? 3, 7. I think my eyesight is failed. I think this is a 5 over here. Let's make that a 5. Okay? This is the point 2, 3. This is 5, 7. Now, what I want to do is I want to find the length of the line that joins these. Now, obviously, one way to do this is to draw this to scale and put a ruler down and measure. But in 3 dimensions, this thing won't work. What we'd like to do is to find a way of doing this which doesn't depend on measuring. Because you see, even if we measure, if these aren't whole numbers, don't these dots have thickness? The best you're going to get is an approximation. So we may want the exact answer. Let me show you where the Pythagorean theorem comes in over here. See, if this is the point 2, 3, and this is 5, 7, if I draw in this horizontal line and this vertical line, okay, this line here does what? The x value is 5 for every point on this line. The y value is 3 for every point on this line. So this point over here would be 5, 3. How far is it from P to R? It would be 3 units, wouldn't it? How far is it from R to Q? It would be 4 units. What are we looking for? We're looking for the length of the line that joins P to Q. Isn't this a right triangle? Therefore, we can use the Pythagorean theorem. The length of PQ squared must be equal to 3 squared plus 4 squared. That's 9 plus 16. That's 25. So if the square of PQ is 25, the length of PQ itself must be the square root of 25, which would be 5. Okay? Another nice place to use the Pythagorean theorem is for something which isn't linear. You know, the most common nonlinear curve that we know a lot about and use extensively in math is a circle. And the Pythagorean theorem is a very nice way to figure out how the x and y coordinates of a point must be related in order for that point to be on the circle. Let's suppose we want a circle whose center is at the origin, meaning at 0, 0, and whose radius is 2. One of the ways of doing this is to take a ruler, put it in any direction, start at the origin, and count off 2 units. See, in other words, I could go from here to here is 2, from here to here is 2, from here to here is 2. They also have something called the compass. It's a pen at one end, a point at the other end. You mark off, you open this up to 2 inches, put this down here, then swing this around, and you see what's going to happen is from the center here to the point that we're looking for, that will always be the same distance. And that's, you see how you get the circle shape over here? See, from here to any point over here is 2 units. Now suppose x comma y is a point on this circle. That means that from here to here is x, from here to here is y. Now, isn't this the Pythagorean theorem again? Let's just take a look at that. This says what? X squared plus y squared has to equal 2 squared. In other words, the algebraic equation x squared plus y squared equals 4 tells you what the points x comma y, how the x and y coordinate has to be related in order for the point to be on this particular circle. For example, roughly speaking, here's x equals 1. I want to find out what must the y value be for this point to be on the circle. In other words, let me see, I can solve this geometrically by just drawing to scale, but I don't know how accurate my diagram is. Let me show you how I use the equation x squared plus y squared equals 4. I say, what point on the circle x squared plus y squared equals 4 has its x coordinate equal to 1? Okay? What point on the circle has its x coordinate equal to 1? All I'm going to do is do what? Use the Pythagorean theorem, x squared plus y squared equals 4, and replace x by 1. 1 squared is 1, and this tells me what? 1 plus y squared is 4. Subtract 1 from both sides, so y squared is 3. So y is positive or negative, plus or minus the square root of 3. So in other words, what are the points? X can be 1, and y can be the square root of 3, or x can be 1, and y can be negative the square root of 3. In other words, roughly speaking, it's 1 comma 1.73. I'll just round off this way. And 1 comma negative 1.73. You may be wondering why you get 2, and I didn't illustrate that before. Remember what I did when I was working on this? I said, let's see what the y coordinate is, but isn't this also a point on the curve? You see, what we're going to do in most math applications, we'll call the upper half of the circle one branch, and the lower half the other branch. And that way, one of the answers is on the upper branch, and one of the answers is on the lower branch. But as long as the diagram is drawn like this, do you see that when x is 1, there are 2 points that belong to the curve? Okay? And by the way, you could ask other questions. You might say, hey, what if I took a straight line like this? I want to find where does that straight line cut the circle. See, geometrically, I can see it. I want to know how that happens. Let's make up an example. I say, at what point does the line y equals x plus 1? See, what line is that? The slope is 1, and the y-intercept is 1. Okay? Intersect the circle x squared plus y squared equals 4. Well, isn't that a simultaneous solution again? See, wherever the intersection is, that point is both where? On the circle and on the line. So for the points that we're looking at for, x squared plus y squared has to equal 4, and at the same time, y has to equal x plus 1. See, we're looking for a point x comma y, for which x squared plus y squared is 4, and at the same time, y is x plus 1. How do we learn to solve this? Since these must be true at the same time, this says what? In this problem, you can always replace y by x plus 1 wherever you see it. So, in the expression x squared plus y squared equals 4, I will replace y by x plus 1. That gives me x squared plus x plus 1 squared equals 4. This is x squared. Now what happens over here? This is a perfect square. It's going to be x squared plus 2x plus 1. And when I add this up, the answer has to be 4. Well, x squared plus x squared is 2x squared plus 2x minus 3. Well, it's 2x squared plus 2x plus 1 equals 4. I want the right-hand side to be 0, so I can use the quadratic formula. This says that 2x squared plus 2x minus 3 is 0. What formula am I going to use over here? What's the formula I'm going to use over here? It's ax squared plus bx plus c equals 0. A is going to be 2, b is going to be 2, c is going to be negative 3. And what's the formula? It's negative b plus or minus the square root of b squared minus 4ac over 2a. And I leave out these steps now because you're supposed to be able, hopefully you'll be able to do this from the previous lesson, but if you can't, it's enough indication that you should review the previous lesson. This comes out to be negative 2 plus or minus the square root of 4 plus 24 over 4, or negative 2 plus or minus the square root of 28 over 4. I could simplify this, but I'm not going to bother. I'm going to look for a numerical solution. I'm going to, on my calculator, enter the square root, enter 28, press the square root key, subtract 2, and press the division sign. See, and what I'm going to find is that one of the places where it cuts the curve is when the x-coordinate is 0.82. The other is going to be when the x-coordinate is negative 1.82. Now, how are the x-coordinate and the y-coordinate related here? The y-coordinate has to be 1 more than the x-coordinate. So if the x-coordinate is 0.82, the y-coordinate will be 1.82. If the x-coordinate is negative 1.82, adding 1 onto that makes the y-coordinate negative 0.82. And now what I've done is I've found where a straight line cuts the circle, and except for the fact that I rounded off the square root of 28, there's no approximation here. This is exact. There's all kinds of ways that the quadratic formula comes up over here. And I'll do another example for you just to show you how this works. But do you see what we're driving at? If you can solve an equation exactly algebraically, there are no approximations, and if you have roots and stuff like that, you can always round that off at your convenience to whatever degree of accuracy you need. But if you can't solve the problems algebraically, what we rely on usually is a geometric approach where we draw the curve, and once the curve is drawn, we use the picture to find the answer. And I'll explain that in more detail next time. But let me just close with, say, one more particular problem. Do you remember, let me see if I can show you. Remember we were dealing with a problem earlier where we were finding the distance, and this was 3 and this was 4. And it turned out that what? X squared was 3 squared plus 4 squared. That's 9 plus 16 is 25. And that's how we got to this side was 5. You know something interesting over here? It was kind of interesting that the 3 sides, the 2 sides in the hypotenuse, were consecutive whole numbers. See, 3, 4, 5. One of the questions a mathematician might ask is, I wonder if this is the only time you can have a right triangle where the sides are consecutive whole numbers. Now, how would you frame that question? How would you frame that question if you were interested in solving this algebraically? You'd say, okay, let's call the smallest side x. Then the other side would be x plus 1, because that's going to be 1 more. And if the hypotenuse is going to be 1 more than this, that would have to be x plus 2. So what we wind up with is a diagram that looks like this. We're saying, let's suppose that one side of the right triangle is x, the other side of the right triangle is x plus 1, and the hypotenuse is x plus 2. What must x look like for this to be true? So by the Pythagorean theorem, what happens here? You have the square of the hypotenuse, that means you're going to square x plus 2, equals the sum of the squares of the other 2 sides. This is x squared, this is x plus 1 squared. If you square x plus 2, that's x squared plus 4x plus 4. If you square x plus 1, that's x squared plus 2x plus 1. So what we wind up with, and I'll just try to write this a little bit bigger, this is x squared plus 4x plus 4 equals x squared plus x squared, that's 2x squared plus 2x plus 1. Now what's the strategy that we're going to do over here? We're going to get, we'll get everything onto one side, make one side equal to 0. That way we may be lucky enough to be able to solve by factoring, but even if we aren't, the quadratic formula is always expressed under the assumption that what? A, B, and C represent the form ax squared plus bx plus c equals 0. So what I'm going to do is I'll subtract x squared from both sides. I'll subtract 4x from both sides, and I'll subtract 4 from both sides. That will give me a 0 on this side, and I wind up with what? X squared minus 2x minus 3 equals 0. Can you think of 2 numbers which when multiplied together give you negative 3, but when added together give you negative 2? If you can't, just complete the square or use the quadratic formula. But if you can, it's not too hard to see what? That what we're looking for is negative 3 and positive 1. See, negative 3 plus 1 is negative 2. Negative 3 times 1 is negative 3. So this factors into what? X minus 3 times x plus 1 equals 0. One of these 2 factors must now be 0. If x minus 3 is 0, x is 3. And if x plus 1 is 0, x must equal negative 1. So the only 2 possible values that x could be are either 3 or negative 1. Now you can't have negative 1 as a length. Lengths are always absolute values. They're always magnitudes. See, in other words, when I wrote down the equation x plus 2 squared equals x squared plus x plus 1 squared, I didn't write down something I was explicitly assuming. What I should be assuming is what? The length can't be negative. The length has to be positive. Otherwise, I don't have a triangle. So you see, what is true is negative 1 will check. If I leave out the x is greater than 0 criterion, if I replace x by negative 1, this will check. Look at, if x is negative 1 plus 2 is 1, 1 squared is 1. if x is -1, -1 squared is 1, -1 plus 1 is 0, that drops out, and we get 1 equals 1. But we don't use that solution because when x is -1, it doesn't obey this condition. But what we've now proven is that it really is astonishing that there are 3 consecutive whole numbers that can be the sides of a right triangle, because what have we done now? We've proven algebraically that for a positive number, the only way x squared plus the quantity x plus 1 squared can equal the quantity x plus 2 squared is that x must equal 3. And this eliminates trial and error forever. We don't have to check anymore. The algebra said, look, the only way this can happen is if x equals 3 or x equals -1, but x equals -1 doesn't survive the membership test that says that x has to be positive. So at any rate, this shows us the Pythagorean theorem, which is important in its own right. It also shows us how we can apply the Pythagorean theorem to applications of the quadratic formula, quadratic equations, and we'll talk more about graphing next time. But until next time, have fun, study hard, stay young. See you soon.